Hi, everyone. My name's Nick. It's my pleasure today to introduce Tanzir, who is my intern for the fall-winter 2023, who's going to be talking about work that he did to improve build times of the Linux kernel. Take it away, Tanzir.
Yeah, so what I worked on today and throughout the duration of my internship was speeding up kernel builds. I focused mainly on automated header refactoring. So what's the problem we're trying to solve? So build times are held back significantly by lexing and parsing. And one of the things that contributes to having more lexing and parsing is having more headers, and headers tend to grow over time. The Linux kernel has been in development for over 30 years, and what we want to do is we want to remove or refactor them such that we include as little as possible. And doing this for something that moves as fast as the kernel is pretty painful, and it's hard to figure out how do you partition a file, what is not necessary, and there's a lack of tooling for this problem in general, so we're trying to just create some tools that people can use to send patches to the kernel to sort of fix the issues. So as you can see here, a lot of the time when we go to build the Linux kernel, we're held back by lexing and then parsing, and this is a very significant part of our build times. So if we can slice these times down, it's going to be very beneficial for how long it takes to build the kernel. So when we go to do our analysis, we see many files become hundreds of times longer when pre-processed. So this means millions of extra lines. So the Linux kernel, when it's fully pre-processed for an x86 def config, has almost 150 million lines or 300 million lines. And that's a very high number. And if we can cut down a few percent of that, that will decrease the load on our lexer and parser, and that just leads to better performance during those phases of compilation and also future parts of compilation. And unnecessary imports leads to bigger compiler IR, and this isn't properly addressed. And this is compounded by the fact that Google builds the Linux kernel very frequently, especially during CI for something like Chrome OS or even in client-built Linux. So these problems are really compounded. So our motivation for thinking that we can fix this is the Linux kernel has had attempts to fix the headers. So Ingo Molnar has been working on refactoring the headers to make them build faster, and his fast headers tree has 50 to 80% improvements, which is really good, and we want that for the rest of the kernel. But the problem is he did this sort of by hand, and the status of the series is unclear because it's been 21 months since his last commit. So we want this to be something that can be continuous and applied to all parts of the kernel. So we want this to not be an issue again, so no one has to create a large patch series like is being done here. So this is where we're going to use automation. In addition to all of that, in addition to just build times, this also helps bisection times and reduction times, and we'll get reduced cloud costs for CI if we build everything faster. And this will increase developer velocity if you have to wait less time. So all of these are external benefits of why we should refactor the headers or why we should lower build times. So this project has four main parts. The first is we want to determine if it's possible to get include what you use to work on the Linux kernel. We want to determine if it's possible to use precompiled headers on the Linux kernel. And we want to find the best way to partition a header with statistical analysis. And four, we want to send patches to the kernel mailing list so we can see how do we use these tools in the real world. So include what you use is the first part. Include what you use is a tool for including only necessary headers. So this is pretty useful. It makes indirect includes direct, and if you have includes that just aren't being used, it removes them altogether. And this is a tool mainly used in C++, but can also be used for C. And since the Linux kernel is large and organized, it's really easy to use include what you use on it. The problem lies mainly in the fact that include what you use is heavily customizable, but it has defaults that don't work out of the box for the Linux kernel, and that results in a lot of problems. So we had to work on getting around that. So some of the problems are type defs like int64t are commonly defined in student. However, that's not really what the Linux kernel does. It doesn't have a student, it doesn't have int64t in the student, and it defines it in types.h. So when it uses its built-in accelerator tables to map int64t to student, we're getting a recommendation for something that doesn't exist. And that's a problem, but it's a problem we can fix by creating our own accelerator tables and saying, hey, if you see int64t, it doesn't map to student.h, it maps to types.h. So that's one problem, but that's another way of getting around it. And when built with a -i, sometimes the kernel uses quotations to mark headers as opposed to brackets. And in addition to those problems, for the majority of this internship, we were using Clang 14, as that's what Linux uses, but now it's been upgraded to Clang 16. Clang 14 has some problems with include what you use. There are some flags missing, but now that it's in Clang 16, this include what you use has gotten better. So now include what you use mappings. Mappings allow us to sort of say, hey, if you see this header, do not use it. Use this other header instead. And this allows us to say, if you see ASM generics, do not use the ASM generic, use the ASM version instead, or use the Linux version instead. And we've been able to generate a lot of these using the kbuild files that are scattered throughout the kernel. And this has sort of allowed us to avoid some bad inclusions. One of the things that we got told when we were creating this include what you use tool is to minimize ASMs and ASM generics, and this really helps us do that. Another problem we run into is macros. So include what you use doesn't know when macros are called, and sometimes it just rips out macros entirely because it doesn't understand where they're being used. So the way we resolve that, it requires a little bit of manual effort, but you can use pragmas to sort of say, if you see this file, if you see this line, just keep it. That requires us sort of putting pragmas all across the kernel, which some people are probably not going to be okay with. So there are other ways of getting around this. And one of the things that include what you use is really bad at doing is macros, or is X macros, which means if code is being generated, it doesn't really understand when that happens. So these cause problems. However, we can get around the macro problem by saying, if you see this other function that is typically called with the macro, or depends on the macro being called, you can bring in this other header instead, which is where the macro is defined. And this sort of allows us to deal with X macros in a way that it doesn't rip them out entirely. And it's really useful because you can sometimes get bad inclusions and prevent them from happening. And we have extensive use of symbol tables throughout the kernel, throughout include what you use. And the only major problem with them is that they must be kept in sync with the kernel version. For example, if we have a function or a struct that is in one file and that gets moved, we're going to have to move it here as well. So that might become a problem later on, but for now, this is the best way to make macros work and to get the best inclusion lists. So once we have everything done, what are the statistics? What did we achieve? For the x86 def config build of libstring.o, we used to have a pre-processing size of 24,000 lines of code. And this was before we use include what you use. once we use include what you use, we get it down to 5,000 lines. So it's 80% smaller, and it cuts the time to build in a third, right? So it removes 0.24 seconds, and this adds up if we use it on multiple other files as well. So you can really save a lot of time. And when we're using an automated include what you use script to just check if the actual code changed, nothing changed except for one line number on a warn on when dead headers were removed. So it seems like there's no negative change as well. So progress so far, we took 220 files, and then we started running include what you use on them. And we found that once we made some meaningful changes, we removed a lot of lines of code, and we were able to shave 3.3 seconds off the build. And this is 300 out of 2,700 possible files that we looked at. So there's significantly greater speed gains to be made, and we've removed over 1 million lines of code. So this is pretty good. And at this point, I presented at the Linux Plumbers Conference as well as the Google Kernel Exchange. We talked mainly about what I had done with include what you use. After these presentations, I worked on a few more items. So the next part of the project is precompiled headers. So precompiled headers can speed up build times, and they're the basis for C++ 20 modules. So we wanted to see, can we use precompiled headers to target some headers that are used everywhere. So some candidates are compiler types.h, kconfig.h, and compiler version.h. They are pound included everywhere because we use dash include in kbuild. And this is the reasoning we had was, if we manage to prevent the need to lex and parse these, since they're used everywhere, there should be some good speed benefits. And we ran into some problems when doing this. So there are multiple different kinds of ABIs with the x86 architecture. There are multiple problems where you have to rebuild the AST file for certain files. You have to rebuild the precompiled header for certain files, which results in errors like, oh, you're building it for x86 64, but your current translation unit is i386. So this has caused a lot of problems. And the one way we got around it, just to test, is, okay, so since we can't precompile for everything, what about we precompile for however much we can? So if we were to precompile as best we can, if we just skip a few things, we can actually build with precompiled headers. It does work. The only problem is it only works with one thread. So when we choose not to include PCH, we're fine, and we have functional build. If we use include PCH, what happens is you're going to have race conditions where one file does not want to include PCH and another file does. And since we put these in Linux include, which is a flag in kbuild, this changes C flags, and this results in a build which works with one thread to break for multiple threads. And so the performance boost from using just precompiled headers doesn't make up for the fact that we are limited to just one thread. So we've determined that, yes, you can use precompiled headers, but it's going to take a lot of time to correctly integrate it into kbuild, especially if you want the benefits of both having a lot of threads and precompiled headers. So the next part of the project is detangling the headers themselves. So the root of all problems here for us is the fact that some headers include a million other headers. They have too many tokens, and they're just not as good as they can be. to fix this, we can partition the headers. So the approach I took was to construct a fully connected graph where each node is a token in a header, and each edge is the number of times two tokens appear in the same file. So after that, we cut this graph essentially in two or sometimes three. We can use any graph partitioning algorithm. I chose hierarchical clustering, and we can partition headers in a sensible way given what the clusters look like. So a brief discussion on graph partitioning. So hierarchical agglomeration is pretty straightforward. So you find two clusters that are the closest together, you make them one big cluster, and if the number of clusters is greater than one, you go back to step one. So just for an example, you can see that E and F are the closest together in the bottom diagram. You make that a cluster. You can see JK, IH, BC are equidistant, but they're all the next closest. So you make those a cluster, and then you repeat this process until you have two clusters, and then you join those two clusters together. So that's basically what hierarchical clustering is. And you can determine closeness in a bunch of different ways: average position, max distance, min distance. So it's a very versatile algorithm. And it gives us graphs that look sort of like this. So you can have this is a basic hierarchical agglomeration of Linux types.h. As you can see, we sort of partition it such that we have two clusters. And within this, you can see that there are multiple smaller clusters that you can sort of take. And looking at this graph, we can have a good idea of, okay, how do we want to partition this header? And one of the things you can notice is a lot of the int types are on one side. So that suggests maybe one of the ways you can partition types.h is by creating a student.h. So now the final part of the project is actually sending these patches. So we made these tools, but we want them to be used, and we want to get feedback to improve how easy it is to use the tools and what the results of the tools are, right? So once we sent our first few patches, we got a bunch of information. So some of the information is don't use ASMs when possible, right? If you can do ASM header.h or Linux header.h, always use Linux header.h. Another thing we learned is find out if you're splitting a separate header into two. Some people wrote that code, and that code might be copyrighted. So find whoever wrote the code and add the copyright there. And another thing I learned is don't remove too much, because sometimes you might just obfuscate the code, and that could result in problems when it comes to debugging. So we have had successful patches. So we broke a chunk of kernel.h into a new header called wordpart.h. We cleaned up a lot of bad includes, ASM generics where ASM or Linux worked instead. And we sent a lot of patches that include what you use to speed up certain file builds. So here's just a bunch of my kernel patches. I think there are 15 of them. Yeah, so a lot of them were just using include what you use, and a lot of them were cleaning stuff up, and one of them was partitioning a header. So now that we have these tools, what do we do next? We can identify header partitions, and we can say the level of connectedness between two tokens, but we don't really have any tooling to automatically act on that information. We need to create something that can do the following. Given a function or struct, identify the component tokens in the header, and recursively identify the dependencies of the components. And once we have that, just extract it to its own header. And this will allow us to quickly get some functional some functional partitions. And after that, it might be necessary to do some human cleanup to sort of check if the partitions are good or can be made even better. And another thing that I realized is it's possible to create automation for this automation, right? one of the biggest things that held this project back was the lack of compute. So better automation and parallelization for the workflow that we currently have is pretty good, would be ideal. So the current development lifecycle goes something like, you identify a bad file, then you improve the include list with include what you use, and then you test for a while. And you can only do this with one file at a time. I experimented with trying to get a Docker image and try and do this for multiple, but the problem that happens there is, well, now if you have one header that you test for 1 hour, you'll have 4 headers that you test at the same time for 4 hours each. So it's like you don't really get too much of a benefit by doing that. So we could improve this by maybe having more cores or more computers. But the biggest drawback to this is the fact that you can only do this is the fact that we have limited compute. So what did I learn? So I learned how to write much cleaner code. My code has improved a lot since my first few commits, thanks to a bunch of the messages that I've been given. So I've learned modern Python. I've learned graph theory and machine learning when it came to try and implement the header partitioning. Hierarchical clustering is something that's typically used in those fields. I learned how to use precompiled headers. I learned how to read C in the kernel. I learned how to read open source C++ when I was trying to figure out how include what you use worked. I learned how to contribute to the Linux kernel, and I learned a lot of Git. I have never rebased so much in my life. And here's the resource to everything that I sort of talked about, my GitHub repos and my my talks. And yeah, that's it.
Awesome. Thank you, Tanzir. We'll give you a round of applause, and then we'll have some questions. I have some quick questions for you. So in your talk, you mentioned ASM and ASM generics quite a bit. Assume some of your audience members are not kernel developers. Can you describe what that is and maybe what some of the conventions are in the kernel code base around them?
Yeah, sure. So an ASM generic file is generally a file that can be included. And when you have an ASM generic file, the actual underlying code can depend per architecture. So when you include an ASM file, the code can depend per architecture, and ASM generics are generally, ASM generics are generally not used because you can just use the ASM version instead, because some files might have the ASM generic implemented and some might not. For example, there's like an ASM generic string.h, or there might be, but if you have an ASM string.h, some files might have an ASM string.h implemented, but if not, you just default to the ASM generic. But here we can say, okay, if we have an ASM, just use it, because a better version for this specific architecture already exists.
So I might find like a naive mem copy in the ASM generic header, and then maybe there's an optimized x86 mem copy in the ASM variant of the header.
Yeah,
makes sense. And then on an earlier slide, you referred to an issue related to double quotes versus angle quotes.
Yeah.
Can you talk to which style the kernel uses and how did you fix that problem?
Yeah. So the kernel uses a mixture of double quotes and angle, but it uses primarily angles. The difference is that sometimes it starts looking in the directory the C file is in to begin with, and then expands outwards if you're using single quotes, and the reverse if you're using angles. The Linux kernel mainly uses angles, and so the way we fix that is by just every time you see a single quote, you can replace it with an angle unless it has a // which implies it's going to a previous directory, in which case it's always using a quotation there. Or if there's no slash, that just means it's the header file is in the current directory. So yeah.
Cool. That's all the questions I had. We'll open the floor to questions. Does anyone have a question for Tanzir?
Have you tried using this on the Clang kernel? or I'm sorry, kernel, Clang code base?
No, we've been focused mainly on using it for the kernel, but you can actually use this on any code base. All you have to do is provide your own set of accelerator tables, if need be. But usually for most code bases, you can actually just use the default accelerator tables. It's just the kernel defines a lot of stuff on its own, so that's why we use custom ones.
Okay.
It was unclear to me from your talk how much of the work for reducing the headers is truly automated and how much manual labor is still required. You know, what automated tools do you use?
Yeah, sure. So if we go back to the workflow, so for the automation, what we do is we identify a bad file, and then we improve the include list using include what you use. This usually takes a few seconds, and then if we see anything maybe that we say is probably wrong or might need to be changed, this doesn't happen super often. Usually we can use the include what you use recommendations. If we see anything we want to change, we can manually change it, and then we can run a few scripts to just test, and that's the process. It's mostly automated away.
How about identifying a bad file? Is that automated?
Identifying a bad file is not automated. What we have is some heuristics of what a bad file might be. So we can see like, oh, this file has this many lines of code. It might be a good target. This file has expanded by 50 times or 100 times. This might be a good target. We have a few scripts to determine that, but it doesn't automatically get rid of bad files. You have to sort of say which one you want to target. But we have a script that does go in order from the compile commands.json and says, okay, this first, this next, etc. So it just goes in order and cleans everything up.
And I think in terms of things that can be automated next, so if you've ever used, there's a utility within LLVM called LLVM extract that's super helpful to be able to pull out pieces of the IR for doing test case reduction. We really, 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 really need a tool like Clang extract to do something very similar, but for a high level layer. Then that's something that we could use to pull out bits of a header file, I think, in a more automated fashion. Will, you have a question?
Yeah, I was wondering if we've looked into adding this to like pre-submit in, say, like Android or in like Chrome OS to prevent like new drivers or new changes from adding unnecessary includes.
Do you want to talk about Boris's feedback this past week?
Yeah. So one of the things we sort of got suggested while we were making kernel patches is this is really this is useful, but it might be even more useful if we had a developer utility that, given a file, just say, okay, this patch could have slightly better headers. Here's how. So this is a suggestion that we could do, and we've been given the suggestion before. I end in a few days, so I don't have time to implement it, but you can run it right now. Sort of like if you have a file, you make a change, and you can sort of just run it on every header in your changes, and it will tell you what could be done better, and it'll make those changes for you. So we can have that. It wouldn't be too difficult to implement.
We had a discussion this past week with one of the x86 maintainers about either integrating this into either build bots or potentially even check patch itself. So one of the parts around this workflow around identifying a bad file, instead of a developer picking a file and running these utilities against them, maybe whenever someone touches a file, we figure out what files were touched, and we simply run this on those files and see, like, we should expect no output or no change. And if we do see an output or some change, then just like, running a file of Clang format, right? Maybe someone needs to amend their patch with some fixes. So that's kind of the goal in the future. I think we can expand this to do that. Any other questions for Tanzir?
So I have a question about so culture and pushing this. So inside Google, we have a culture of include what you use and don't have like one central header and that expand to like 100 include. I'm not familiar with the Linux kernel's culture around this. Have you run into that? And if I think, for example, QEMU I'm more familiar with, they do have one of those giant header files. Did you run into some people have that kind of philosophy and resistant of this kind of direction?
Yeah, so actually, so the kernel does have some like gigantic headers, but the general philosophy we ran into was people want to sort of partition those headers. So one of the things I was suggested on my first patch was I was recommended to include what you use was recommending I keep a gigantic header, and someone suggested, hey, this header is pretty big. Maybe you can cut this header cut this part of the header out into a separate header while you're making these changes. So the philosophy, from what I've seen in the kernel, is generally people want to move away from big headers.
There's definitely a lot of interest. I would say right now the kernel doesn't have an explicitly stated policy around direct versus indirect includes. And so right now, half the battle, I would say, with sending these patches is around education, around the benefits of this approach. It's a little tricky for folks that have been, working on the same code base for 30 years, but more work for us to do to help, persuade people about the perceived benefits. So, we were just discussing it on LKML this morning with people, but I think having a stated policy is something in the future where if we can point to that in the coding standards, that helps end a lot of these arguments like very early on, kind of thing. So
another question about, so I feel like I don't know if there's a tension between splitting into a lot of smaller header and the precompiled header. What if you just have one header? Every file only ever include that one header, and it's precompiled. What kind of trade-off are we looking at here?
So one of the problems we run into is that there's a lot of macros, and especially when you go to ASMs and ASM generics, you might have multiple definitions of the same function. So you need multiple different headers to actually build the Linux kernel, because like if you have 3 mem copies, 2 are declared in ASMs and 1 is declared in an ASM generic, 2 of them are getting overridden, right? So
right, I'm thinking of like if we just have one file called Linux kernel header.h and include all other Linux header file are included in that file.
Yeah,
including all the relevant ASM architectural thingy, and all other C file only ever include that one header file.
Yeah.
That kind of situation with precompiled header, what's versus the current, like we try to slim down on header file, what's the trade-off?
The trade-off, if I had to guess, is probably that not a lot of people would want to do that because one of the things we noticed is like people tend to move away. Like if we try including one of these big headers, people are generally dislike that, right? So I wanted to include this header, which was pretty big, and then someone was like, don't include it, just try and break it apart if you can.
Right.
I think it would be an interesting idea. Like you could do something like try to cat a bunch of .h files together, like as part of the build system itself.
Yeah.
Like have some custom rules to say like cat a bunch of .h files together, precompile it, and then have everyone just include the precompiled result as a thing. So it's probably an interesting experiment to try in the future, kind of thing. I'm sure it's doable. To the point about the multiple ABIs, and the reason for that is, if you're familiar with the boot process on x86, we actually have object files that are compiled for 16-bit, 32-bit, and then 64-bit. And all the precompiled header stuff, like, is the compiler is super unhappy when it sees like you change one command line flag between translation units, and it will just explicitly reject the precompiled header, whether it's safe or not. It is conservative and says maybe one of these flags affects the ABI. I don't know. Usually they don't. Sometimes they do, kind of thing. And I think that's one of the trickier parts about K-build integration, the kernel's build system, where even if we could generate one mega header, we still might have to precompile it 3 or 4 times, depending on what part of the ABI, because then you have like the VDSO as well as built into the kernel, but that's like a user space ABI.
But like you compile one header 5 times and then load the AST everywhere
Mhm.
versus have to tag lex and parse everything. I don't know. Maybe you try that.
Yeah, we ran into a lot of problems with just getting precompiling to work with 1 or 2 things that we decided not. That was an idea I had at the beginning as well. Why not just precompile everything? And we never got to try that experiment out because there was just so many problems with getting precompiled headers to work.
Any other questions for Tanzir? What's the most interesting non-coding thing you learned about contributing to open source projects?
Yeah, so I learned how to set up an email client. That was yeah, I didn't think I'd have to do that ever, but I learned how to do that. It was weird. Yeah.
Cool. All right. If there's no other questions, let's have one final round of applause for Tanzir. Thanks, Tanzir.